Have you ever just looked around and wondered what everything is really made of? I mean, your desk, the air, the stars, all of it. Well, it all boils down to one tiny fundamental building block. Today, we're going to dive deep inside that block and explore the architecture of the atom.
Right, so we all learn in school that atoms are the basic units of matter. But that's really just the cover of the book. The real story is what's actually going on inside. So let's peel back the layers and take a look.
To really get what an atom is, you first have to meet the main players. It's kind of like a team, this atomic trio of particles that builds, well, everything you can see.
And here they are, the proton, the neutron, and the electron. You can kind of see the whole layout right here. You've got two heavyweights, the proton and neutron, packed together in the center, which we call the nucleus. And then you have this incredibly lightweight particle, the electron, living way out on the fringes. Oh, and AMU? That just stands for atomic mass unit. It's a super tiny unit of weight we use for these tiny particles.
Okay, first up, the proton. This is the positive force in the atom. You can think of it as the anchor, sitting right in that dense center, carrying a positive charge and a pretty big chunk of the atom's mass.
And hanging out right there with the proton is the neutron. And just like its name suggests, it's neutral. It has zero charge. It's kind of like the proton's roommate. It adds mass and helps keep things stable, but it doesn't change the overall charge of the nucleus.
And finally, you've got the electron. This little guy is the energetic one, with a negative charge. It's the total opposite of the proton and neutron. It lives outside the center, and it's so incredibly tiny its mass is almost zero. It's just this little bundle of negative energy constantly zipping around the core.
All right, so we've met our three particles. Now let's see how they all fit together. We're going to start with that dense central hub where the protons and neutrons live, the nucleus. So the nucleus is basically the atom's command center. It's got all the heavy particles crammed into an unbelievably tiny space, which means it contains almost all the mass and has this strong positive charge. It is so ridiculously dense that if you could somehow scoop up a piece the size of a sugar cube, it would weigh billions of tons. Seriously, the apple core analogy is perfect. It's impossibly small, dense, and right at the heart of everything.
Okay, now let's travel out from that tiny core into the huge, open space that surrounds it. This is the electron's world, a space we often call the electron cloud or electron shells.
Now, it might seem like total chaos out here, but it's actually a very organized system. Electrons are stuck in these specific energy levels. And here's where it gets really weird. They don't orbit like planets. It's more like they exist in a probability cloud, a region where they are most likely to be found. And what this really means is that an atom is almost entirely empty space.
And here is one of the most important rules in all of science. These shells have capacity limits. The first shell, the one closest to the nucleus, can only hold 2 electrons. The shells further out can hold more. This one simple rule is absolutely everything. It's the entire basis for all of chemistry. It dictates how atoms connect with each other. Okay, so we have our protons, neutrons, and electrons. But what makes an atom of gold different from an atom of oxygen? I mean, they're made of the same exact stuff. Well, it turns out an element's entire identity, its very soul, comes down to just one single number.
And here are the two numbers you need to know. First, the atomic number. This one is the big one. It's simply the number of protons, and it acts as the element's unique ID badge. If you change the number of protons, you literally change the element. Then you have the mass number. This one's much simpler. It's just the number of protons plus the number of neutrons. It basically tells you the total weight of the nucleus.
So all this theory is great, but let's put it into practice. We'll use a famous element, one that's absolutely essential to life as we know it, carbon.
6. That's it. That's carbon's fingerprint. This number means that every single carbon atom in the entire universe, no exceptions, has exactly 6 protons in its nucleus. If it had 7, it would be nitrogen. If it had 5, it would be boron. 6 is carbon.
Now, the most common type of carbon has a mass number of 12. Remember what that means? It tells us the total number of heavy particles, protons and neutrons together, that are in its nucleus.
So here's where we can play detective. We know the total weight in the nucleus is 12. And we know from its atomic number, its ID card, that exactly 6 of those particles have to be protons. So the question's pretty simple. What's left?
Yep, the math is as easy as it gets. You just take the mass number, 12, and you subtract the atomic number, 6. The answer is 6. So, a standard carbon atom has a perfect balance, 6 protons and 6 neutrons.
So, we've taken the atom apart, we've looked at all the pieces, and we've put it back together. But why does any of this matter? Why is this tiny architecture so important? Let's connect the dots.
So here's the bottom line. First, everything in the universe is built from the same 3 particles. Second, an element's entire identity boils down to just its proton count. And most importantly, the specific way those particles are arranged, especially those electrons in their shells, is what dictates absolutely everything about how that element behaves.
And this is the real payoff. This whole invisible structure, it's not just random trivia. It is the rulebook for all of chemistry. The reason water acts like water and iron acts like iron is all because of the unique internal architecture of their atoms.
So we'll leave you with this final thought. We've just looked at the blueprint for a single atom, a structure that's almost entirely empty space, running on some very strange rules. Now just think about how trillions upon trillions of those tiny blueprints combine to build everything you can see, touch, and feel around you. That, right there, is the power of the atom.